Today we explore how a Hyperloop actually works, what has been demonstrated so far, and what it will take for the public to ride it, from physics and prototypes to business models and realistic timelines. Welcome to Elemental Science Magazine. A Hyperloop combines a low-pressure guideway, a contactless lift system, and linear electric propulsion. The low-pressure environment reduces aerodynamic drag, allowing a streamlined pod to travel at high speed with moderate energy use. The guideway is segmented with isolation valves for safety and maintenance access. Pressure environment. The 2013 Hyperloop Alpha paper proposed operating at a pressure thousands of times lower than ambient atmosphere. This cuts drag dramatically but imposes structural stresses and requires vacuum pump systems across long distances. The design resembles a pipeline more than a railway, though it must safely transport people or cargo inside. Source: Tesla. Propulsion and power. Linear induction or synchronous motors are typically embedded in the guideway, with the vehicle carrying reaction plates or magnets. Power demand peaks during acceleration and drops during cruise. Braking can switch the motors into generators, recovering part of the energy as heat or electricity depending on the infrastructure. The Alpha proposal envisioned frequent departures of small pods rather than long trains. Levitation and guidance. Most current prototypes rely on magnetic levitation for smooth, contactless lift and lateral stability with minimal moving parts. Early designs explored air bearings using compressors, but magnetic systems have proven more reliable at high speed and easier to maintain. Comfort and ride quality. Acceleration targets are kept within urban transit or aviation norms, typically below 0.5 g, to maintain comfort. Track curvature must be very gentle, meaning route geometry resembles that of high-speed rail, but with even tighter tolerances due to higher design velocities. What has been proven in the real world? In 2017, a Nevada test facility integrated vacuum, levitation, propulsion, and control systems, achieving triple-digit km/h speeds with a full-scale pod. In 2020, 2 passengers rode in a depressurized tube at roughly 172 km/h over a 500 mm test track. This validated basic human safety interfaces but remained a short demonstration, not a transport service. Newer testbeds. In March 2024, the European Hyperloop Center opened a 420 meters tube in the Netherlands designed to demonstrate lane switching and core subsystems. Public levitation tests began in 2024-2025. The project's purpose is to support standardization and safety validation for European certification efforts. Asia's speed records. In early 2024, China's CASIC program reported a superconducting maglev test, reaching 623 km/h inside a 2-kilometer low-pressure tube at Datong, Shanxi. The results represent one of the fastest controlled runs in a partial vacuum environment, though these were research trials without passengers. What remains technically hard? Large-scale evacuation procedures in a low-pressure tube still require full demonstrations. Civil works spanning hundreds of kilometers with consistent tolerances, valves, and pump stations must be industrialized. Reliability, maintainability, and safety levels comparable to aviation are essential. Regulatory standards are now under development, particularly in Europe. Engineering summary. The engineering framework is technically coherent and early prototypes have validated core functions: vacuum operation, levitation, propulsion, and limited human testing. The main gaps are industrial scale-up, certification, and cost. Progress will depend on incremental testing, likely beginning with freight or short-distance pilots before any passenger deployment. Transition. With the technical foundation outlined, we turn to the realistic pathway, timelines, business structures, and what an initial public route could look like. Origins and vision. The modern Hyperloop concept was introduced publicly in 2013 with the Hyperloop Alpha paper proposing a Los Angeles-San Francisco route in 35 minutes. That open-source release sparked global experimentation and defined the performance targets that continue to guide today's research programs. Early milestones and lessons. The 2020 Nevada human ride demonstration confirmed basic safety controls for people inside a depressurized tube, but highlighted how far commercial systems remain from operation. The company that led that test later shifted to freight development and ceased operations in 2023, illustrating that technical success does not ensure economic viability where progress continues. Europe's 420 Menor facility focuses on component validation and certification frameworks. In China, CASIC's superconducting maglev tests continue to push high-speed performance boundaries. Together, these regions now lead global Hyperloop research, while most U.S. activity has paused following company closures. Projected timeline. Analysts and policy documents suggest a phased path. Late 2020s for freight or mixed-use pilots, early to mid-2030s for short passenger demonstrations, and potentially mid-2030s onward for limited commercial corridors, if safety, reliability, and regulatory frameworks are proven. Some studies project even later adoption. First public service concept. A plausible early route would connect an airport with a logistics hub or nearby urban node, optimized for straight alignment and gentle curves. Operations would use small pods dispatched frequently rather than long trains. All systems would be electric and autonomously managed, with ticketing modeled on air or rail systems. Business models. 3 approaches dominate discussion. Publicly funded infrastructure operated by private concessionaires, similar to toll roads. Freight corridors co-financed with logistics partners valuing speed and reliability. Licensing of Hyperloop technologies to local consortia that finance, build, and operate region-specific systems. Pure venture capital models have proved unsustainable. Enduring projects will require public-private partnerships and institutional support. Risks and costs. The largest expenses are civil works, land, pylons or tunnels, pump stations, and energy supply. Higher speeds raise power demand, so operators may choose sub-maximum speeds for efficiency. Demand uncertainty and regulatory ambiguity remain major risks, as Hyperloop does not yet fit within established rail or aviation frameworks. Signals to monitor. Progress at the European Hyperloop Center and advancement of formal safety standards towards certification will mark key steps. In China, track extensions and verified higher speeds would demonstrate scalability. The strongest signal will be a financed, shovel-ready pilot corridor with an identified regulator and validated evacuation plan. Conclusion. The modern Hyperloop vision gained momentum in 2013, and the first passenger demonstration occurred in 2020. Large-scale public service is unlikely before the 2030s, given the need for standards, funding, and industrial readiness. The underlying physics are feasible and core technologies have been demonstrated, but the decisive challenges are regulatory, financial, and logistical. If freight pilots achieve consistent, safe operation and certification frameworks mature, Hyperloop could progress from test beds to limited commercial use. Until then, credible evaluation should rest on verified tests, transparent funding, and published regulatory milestones. Thanks for watching Elemental Science Magazine.